Yeah, welcome back to Cloud Computing and Big Data. Today, lecture 3 and the second part of it. So in the first part, we looked a little bit on the basics of Apache Spark, in a way complementing lecture 2, where we focused solely on machine learning. And in the first part, we really learned a little bit what the Spark core entails. So it has concepts like the RDDs for data. It has also different fault tolerance options we will talk about later, of redistributing tasks. It works together with head nodes, with worker nodes. So what you saw in the video with the master-slave architecture is actually something which is not anymore used. So I didn't remember that. So you should use master-worker, right? So that is now the new term for it. However, it captures the essence what we discussed. There are just a couple of masters, maybe 2 in the head nodes that take care, are the managers of all the work. And then the workers can scale up, can scale down as needed, have all the executors that would Spark then automatically split off. And this is one of the benefits we also were discussing outside. So when you do MPI, high performance computing, all of these applications in this area are really explicit message exchanges. You have to program yourself what cores you want to address in this communicators. It's a concept called MPI communicators and so on, which means you have much more, let's say, application code that goes into communication aspects of saying who is allowed to see which messages to then operate on it. Another notion we found in the break quite useful here, I think, is also to think about, again, the high throughput character, right? Divide a big problem. That's why you want to use Spark. And then later on, you conquer it and join a small result, right? Again, if you have lots of communications in Apache Spark, that would be not a good idea between the different workers. Of course, each worker should operate alone on a chunk of data, taking data locality in mind on the disk, but also on cache, as we've seen in the video, and then report the result. And the manager and the other programs will then make sure that this is actually combined to a real solution. Now, for the second part, we want to understand a little bit how now applications can leverage these core elements. We have seen already that Apache Spark actually nicely supports 4 different classes of applications, which are not only machine learning, we already touched on, but also streaming, SQL, and then also graph problems. And this is something now we want to explore a little bit in the second part of the course. Now, when we look now on a very simple idea, basically, which is quite known, people have heard about the word count application, maybe. I don't know, here in the class, it's the number 1 example, basically, of Hadoop, the word count, which shows the essence of how quickly you can actually go through data. Now, when you see here, of course, the interesting aspect I have here on the left, bottom left here as an example, think about that this should be done on petabytes of data sets, right? Think about Facebook accumulates, or the other big tech giants and so on, and social media accumulates a lot of data. And then a simple word count could be actually already loaded, right? Or filter data on politics, on harassment, which is an important part, to remove maybe posts, for instance, in Facebook, things like that. They have to go to a hell of a lot of data. And by doing this in simple map-oriented ideas of just counting, right? There's no big computation. You see here how that works a little bit is like you have this different phrases of texts, could be maybe a couple of terabytes in this chunk and a couple of terabytes of data in this chunk. And what the map task here will do is essentially just count the occurrence, right? Okay, I found another 2, I found another B, I found another OR. So a big, large array, which essentially is just 1, 1, 1. Okay, I found something, I do this. There's no big computational complexity in this. Hence, it's actually quite quickly executed. And then you have a second step, and this is something which will be also alluded in lecture 5 when we talk about shuffle, sort, reduce, because it will do some sort of magic, reducing elements by a certain key. And when you specify this key correctly, which is here in our example now, of course, a word itself, you would see it will then reduce it by the keys on all these different map outcomes, and will then come to the overall count of saying, hey, B was actually 2, not was 1, etc. Or was 1 and 2 was 2. Yeah. So, I mean, this is a simple application. The interesting thing now and takeaway message for you is it is programmed, for instance, in that way, right? If you now hear what to have the Hamlet, you know, this text from Hamlet, is a Prince of Denmark, actually. It's an interesting book you have to read. But when you want to just implement this, you have 3 lines here to have this implemented. So this is already quite an achievement, and you don't have to think actually about all of this here in the messaging. So all of these different workers, in other words, that you see here on the other side, right? So now this is the interesting aspect. While you implement it just very, basically on a flat Python level, again, the inherent parallel aspect, the Spark, context will break it apart and will then create this kind of duck that you've also seen in the video. And if there's not a duck which is nicely here, because we can nicely actually parallelize it across all the different data blocks. And then, of course, taking even cache into account. And you can continue and continue. You can see, as we've seen this transformation actions, there are lots of opportunities, how we can move, work on the data, change the data, or perform certain actions on the data here for counting and so on. Hence, it is a user-friendly approach to parallelization, right? People that have no idea about HTTP ports, about communication exchanges between what's happening between driver, worker, protocols, TCP, HTTP, there's lots of things going over the wire. This is just beautiful. So machine learners can just focus on that, do their job, and rely on the technical people somewhere of just implementing Python code. And the benefit comes, and we discussed it in the break, again, big data, right? So if you want to really scale, you can use scikit-learn maybe for many things, also in machine learning. But when you really want to scale beyond your little laptop, then Spark is really good for you. And the inherent scaling, you will never really need to know, right? This is something what the people, the CTO or whoever is actually swiping the credit card for you in the cloud will do. Now, thinking about how that all came along, we discussed again in the break, this is sort of a Hadoop second and better version of it. However, Hadoop has many inherent concepts which are in the distributed file system still used, also together with Spark. But one of the benefits of Spark is really to have this different libraries which are optimized with it, with the core already inside the distribution. Let's say in former times, we have done lots of other things, like Hadoop, for instance, is giving you just a MapReduce engine, right? So on top, we have used Mahout, which is a machine learning library on top of MapReduce. And then another framework, which is error prone of combining more and more and more of them. It was working, but needs more massaging. And having this, let's say, inherently supported, this kind of 4 big application classes really that are often with data sets. And this is really the SQL. Many people have still structured query languages. Do you know actually what SQL is? Do you have heard about data warehousing, data sets, right? So this is a relational database. Everything is nice and shiny. You have basically all your different schemas, and you can query that with a powerful SQL language. Still lots of things using that today. But still many people use streaming approaches these days, especially more in social networks, where maybe not everything needs to be directly taken or cared for, or you want to filter, we will make a case for it. Graph problems are inherent. I mean, basically you can see Facebook as a big social media graph, right? Where who is liking who, which posts, and so on and following. And then hence there's some applications also in this area. And by supporting all these different classes inherent in the Spark engine, and then of course you can imagine there's instead of going to all these different implementations, it is also optimized for in-memory computing again. So this is another key differentiator, what made Spark quite the successor of all these different products. Hence, it works still, however, together with some of these Apache products. Here's a good example. I think the SQL library, if you see here, when you have the traditional Hadoop and was doing this with the MapReduce engine, and you want to basically have here an SQL statement, very simple from people, and map that to a certain idea of names, doesn't matter really. You would have, let's say, quite a difference between Spark SQL and Hadoop. Again, ideas about the performance, of course, doing it in memory and so on. Of course, if you don't have strong memory, we were discussing that outside, if you do both on your laptop, Hadoop and Spark SQL, chances are that the performance is almost equal, right? Because the memory might be not perfect, and hence you have to do lots of reads from your own hard disk. This is again coming up again and again, of course. Hence the Spark SQL library is quite nice and can be nicely combined with other SQL-like languages like Presto and these elements. Now looking on basically PySpark and how we, for instance, will use that also in the assignment and basically in practical lecture 3.1, you see that it's also straightforward, where you have some idea of importing this here as certain basically ideas of the PySpark engine that you can then easily import with the different libraries. But also you see PySpark.sql functions types, which are basically then already alluding to the SQL runtime of Spark. And if you here then go further, I left here some elements out, you see how that now is here in the SQL sort of way shown in the data frame exactly with the different IDs. And you can imagine you can now do select statements based on that. But of course, it is a misleading example that this is a very small data set. Think about, again, this is scalable now to very big data sets where the benefit would rely. Otherwise, you maybe use, a typical Apache, kind of typical relational database provider, like Oracle, for instance, or so. Good, coming to streaming. Streaming in some sort is different from the SQL idea, and the idea is the velocity to support, right? So here's the idea is you get lots of elements, let's say Twitter tweets coming in, you want to analyze them with your company very quickly. Is someone talking badly about my product? And you can actually buy the Twitter library to get access to all the tweets and so on, and you can run them through. And so is someone talking about my product, could be also positive or negative. We call that machine learning sentiment analysis. You can analyze the words, and then by analyzing this, you can actually see if it's negative or positive. But that's just the application behind it. The interesting thing is, again, what you see on the idea of the actions transformations, that in one way, you have the stream directly supported, coming basically through the Apache engine. And you want to have here a filter, let's say, containing Spark as an example, or your product. And then you basically have a very couple of essentially lines to do that. And you have no idea where and where the Twitter, idea of the data is lying around. You have a very, of course, notion to first downloading this and getting access to the Twitter utils. And this is probably something what a manager would do for you, a CTO in this regard, for again, doing the technical details for you. You as an application developer, you are still on the Python level and work with a streaming API and can do lots of different things. Again, another benefit, as we discussed with the node and RDDs, you see the node crash right there in the middle. And again, all these libraries also benefit from this fault tolerance idea. Right? So if there's a node crash at a particular point in time, it would reanalyze and redistribute the time series data set that you have there to see, was it basically the data there? Again, this is also a very, let's say, robust idea of having this interesting streaming library. And there are many different tools about Apache Flume, for instance, that you can combine it with, that we had in previous courses. But yeah, in the sake of integrating some new elements, as we said, with hyperparameter optimization and so on, we had to also get rid of some of the things. But it's very powerful. So then coming to machine learning library, that is, of course, having something done there already. You know a little bit the meaning from lecture 2, but we will do this also in lecture 3.1 a little bit with logistic regression. But you can imagine, and this is now another benefit of these libraries, that they're quite nice algorithms. But the beauty here in this is they are parallelized, right? So in other words, if you use scikit-learn on your basically system, you can still do logistic regression. You can do lots of different tools, but they're not parallelized, right? They will be sticking already serial. Even if you put them on the cloud with tons of different cores, it will be still executed in serial. No benefit, right? So hence, where people sometimes use it also, maybe even in serial environments, would be the implementation of some of these algorithms. I was talking in the break about recommender engines where we even use this, right? Alternatively, squares, where you want to understand in shopping behavior, maybe who is actually a person like me, which is easy, but maybe it's like more important that person like me that also bought things like me, elements. And these algorithms are all implemented in the mlib for distributed aspects, right? So for really huge data sets where, for instance, scikit-learn and other serial algorithms will fail. And this is stretched across the different disciplines of machine learning. I brought you another example, is what K-means clustering. Have you heard clustering perchance? Okay, some of you, good. There are different ones, K-median clustering. So just shortly, you see a little bit the video here. that it finds essentially the different clusters. So here we have a different situation than classification. We don't know what the classes are. We just have a bunch of points somewhere in the space that you see at the beginning of the video. And the k-means is now the idea of saying, can we find essentially different clusters out of it? And it uses so-called similarity measures, could be Euclidean distance, for instance, a ruler distance. Here, for an example, you can see at the beginning of the video sort of have a kind of idea that maybe there become 3 clusters, right? And by specifying now the k, and this is the different colors, this algorithm can actually do this by getting more and more to this Euclidean distance and working through it. And this can be done now on a petabyte of data with large data sets, incorporating lots of features, which is a very strong argument of using Spark, for instance, has this kind of nice distribution. Of course, we have an MPI, also one solution called HeyDBScan, which I think in the moment from my research, it was one of the most scaling algorithms, but it uses different aspects. For instance, we don't have to specify the number of clusters, the k, in advance, which is a disadvantage of this algorithm. So here we sort of need to know already how many clusters are there. So 4. So I specify 4. In HDBScan, for instance, another one where you have not determined this, but it has other problems like, not convex problems like bow tie cluster type will be not found and so on. So hence all these different algorithms have their benefits, advantages, and so on. And if you want to use the MLlib, it's really good in this different clustering algorithm, in simple classification, but also in this kind of scalable recommendation engines, which usually fall behind a little bit in other packages, right? Because it's quite a commercial idea of doing recommendation engines and so on. And that's why actually the Spark is much better than academic solutions, for instance, using MPI usually. Good, and we use that more. Still, again, the message goes the same way. On the right-hand side, you see actually what you have to do is a very simple idea of getting a data from HDFS, a Hadoop distributed file system, read it in, maybe with a map task, parse the points, and that's one line. And then the other says k-means train. Of course, you have some import statements to do. You can imagine from the MLlib to get into the Spark or in Python. Of course, then the kind of k-means to be used, and that's all what you do. The distribution and everything underneath is coming from the Spark context from the driver, and then will activate different workers depending on the situation. Good. Yes, if there are questions, of course, let me know, right? You can raise your hand. Maybe sometimes the distributed nature of it is not really clear, but we have also time for questions every now and then, please. Sorry for this, I am a bit biased. So the student asked what MPI is, rightfully so. It's a message passing interface, a bold name. It stands basically for the advantage on high performance computing in applications. You, as the name suggests, do lots of message exchanges. So message passing means you have basically the key idea in each iteration of the applications, let's say weather forecast, on each of the different areas, you would maybe have the complete Reykjavik tiled in different pieces, Cartesian, could be anything. But in each of the different second of, basically predicting the weather, you have lots of physical variables to exchange. It's not high throughput. It's high performance computing because the physical variables are always interaction with this. How much rain here affects the next tile, and so on. So this communication needs a specific, very powerful library, which is MPI and which is actually a bulk of the high performance computing course. It's still distributed, but lacks completely security because basically it's inherent a cluster, right? You should not have MPI now between different Spark or work engines, for instance, communicating. So it's sort of another domain. However, it is parallelizing a lot. And through effective network interconnects called InfiniBand, what we have in HPC systems usually, which are a very expensive part of the cluster, you can have also then the communication extremely fast, right? Where of course Apache Spark would be then quite too slow. Hence, there are certain application problems like this one in weather forecasts or other that are much more physical, like smoke evolution in this room, for instance. These are things, physical computational fluid dynamics problems, as it is called. These are used traditional MPI and will always remain with MPI. There's no chance that Spark can do it better because mostly the many interaction it needs. You cannot break down the problem and say the smoke is just in this room and the smoke is just in that room. And for an hour, I don't care. And after an hour, we will see how the smoke maybe comes. So, right, it interacts a lot with the wind, it interacts with lots of physical elements which affect also the other part of the simulation. But good question. I come traditionally a lot from high performance computing after 20 years. So whenever I have a term or so which is unclear, just raise your hands and I try to explain it. Hence, in this course, we don't talk too much about MPI. We will come back to MPI, interesting enough, in deep learning. So there we will have seen something like distributed deep learning when you want to do this at scale. So really using many, many GPUs inherently for the gradient update, which you need to do for learning from basically for deep learning networks over many, many neurons, you need an average. And this average is actually communicated with MPI. So hence the statement for deep learning networks we will talk about in lecture 6 and 7 is then basically a bit different. There we need really powerful MPI. And with this, the impact of clouds is there also a bit more limited. You need HPC clusters within the cloud, which are really having this performance. Right, good. Coming back a little bit to our machine learning library, I just wanted to come back to the example we had already, but we will see logistic regression stays with us also in your assignment 1, for instance, in lecture 3.1. I will demonstrate it again to you. But by now, I think you have learned a little bit the idea of this iterative approach, right? Which is quite nicely to see that you can boil down a problem and basically optimize it as it is here. The SGD idea of an optimizer, you don't have to use it. There are different other optimizers using, for instance, momentum, even if you go downhill here in the error surface, as we discussed last time. And this is something which is also used in this logistic regression, but also shows you then the iterative approach that you have. By iterative, I want to come back here now again. When you always have to iteratively update the weights, of course, you iteratively go to the same data, right? Over each time you learned, okay, several things. You perform the weight updates as we discussed. You maybe come a little bit to the optimization a bit better, but you touch the same data in the next iteration. Hence, the cache idea from Spark is quite brilliant for machine learning, right? Hence, many of the performance elements, instead of doing HDFS read and write again, remain true for these examples. But this is simple machine learning, where it works well. Again, when you talk about deep learning network, distributed deep learning, in lecture 6 and 7, we have to go another way. So it's not so good there. And the same is true for k-means clustering. If you think about the k-means clustering as an example here, again, you see the performance. Why machine learning algorithms essentially have so much good performance in that? Because essentially machine learning means nothing else from learning from data. And if you really want to do it bluntly, you say learning iteratively through data, because you usually don't go in one shot through all the data and have the solution. Statisticians can do this sometimes with some tricks in regression. It's simple learning models, if you call it learning, but mostly it's more representation of the data. Hence, we're interested in this iterative walking through, and there the MLlib is just beautiful for all lots of different application domain problems. Right, and of course, as I said to you already, there are many elements, tree-based ones we didn't discuss. Decision trees, and usually today nobody uses decision trees. They use random forests, so you will not actually do one tree, you do 1,000 trees at once, and then prune them at different elements and so on. And these random forests are also quite nice, implemented in the machine learning library, again at scale. And this is also one of the benefits alongside clustering. And I was alluding to, alternating these squares, which is, for instance, recommender engines and so on. Now for regression, simple regression tasks, you would say, well, as scikit-learn is still maybe a better approach. But if you're swimming in big data, scikit-learn will probably not work on your little laptop. So hence, you still have to go there, even if the application domain problem is relatively simple, like binary classification we did with regression techniques. You would say, well, for the computation, we don't go to clouds, both for the capacity and for the idea of working with large quantities of data, which is the other half of the course. However, we go a bit more into the MLlib also with our lecture 3.1 in the future. And then for the end of this lecture, basically now, we want to focus a little bit on the graph library here that is also posing an interesting basically problem, but I think many of you have heard from the basic page rank algorithm, right? So things like in Google, how it began, Google Beta, I remember still this, you can't believe it. When I was going to Google, it was still Beta. So today they have tons of services, but yeah, they went actually very successful with their ranking of techniques. And what sounds like finding the top 20 pages in the internet is so simple, and by now people have actually modified this algorithm. So there's so more features that are actually going alongside the site, right? It's not just what we will discuss now, but it'll show you a little bit two things. Firstly, that sometimes a table seems to be not the right thing to do, right? So if you think about now how the web works, like social networking, the same with the typical internet and ranking them, the sites, you could imagine that a table view would be quite sort of misleading some aspects. And you can still do that and still can work with it. And of course, there's a certain point to some of the column stores. That's something which I also put out here of the course a little bit, where then they benefit again from the table view if you don't have, let's say, always the same information for the data. But this is a little bit now out of scope. Let's focus on the graph idea of the web. And basically, this is a thing where you basically can look at the interconnected elements a little bit more sharper and think really about your neighbors. So who are you actually referring to, or you are referred to from? So basically your neighbors in terms of, getting a link or getting a link to the outside world. And still sort of a very simple application problem can have many different elements. Like you want to basically have these kind of web pages that claim to be, let's say, the biggest brokers, or let's say have a very, let's say, key idea of getting lots of attraction with lots of search engine optimization, SEO techniques, for instance, and so on. Still, the web engines are actually not fooled necessarily only by these points, but also by the popularity. And the popularity is something that you have to compute on the pages. It's not so easy. Again, from graph theory and so on, we discuss here now a few formulas which are not so important for you to take. It's about, of course, you can imagine the graph, it has a sink, and it has also then, of course, the other way around, the vertices, the little big fellows here. And then you want to understand now, basically, what would be the most popular website to rank them, right? Or more popular and so on. So in a way, you would say that sounds like a very trivial problem. But when you come to the computing of it, of course, think at scales, right? With millions, billions of URIs and HTTP addresses and so on. This is not so trivial anymore. Hence, the people that do this, they have to sort of score engine behind it. So what are you doing in terms of ranking this? And this is again something where you think, okay, we could do this maybe once, but in a way, we don't know this big smiley here, right? So in this sense, also because it could be different relevance of people or of different sites here, really, right? Sorry for the smileys in a way. It stands, of course, for sites, where you say it's maybe much more relevant that this, big blue fellow here is pointing to you. This could be the University of Iceland, or just me, as Morris as a small professor somewhere pointing to this, right? It has much more hits, it has much more visibility, people using that, it has a higher rank in itself. So in this sense, we're going here around a corner, so to speak, right? Over one vertex more, that a direct computation of the popularity would be misleading. Hence, this is a beautiful approach, again, showing you that iterative computing is not only basically machine learning, as we discussed, or boiled down the error, right? With what we did in linear regression, then in logistic regression, iteratively get the error down by comparing more examples, updating weights again and again. Here, we're sort of not really interested in that particular problem. We want to have the popularity. And there's this algorithm PageRank, which is one of the, let's say, foundational algorithms. And you see many, of course, adoptions to it and modifications of it. But if you now start this and say you would initialize this with all one, you see in this little bit trivial example. And then when you put that to Spark, you see really how nicely this can be executed on Spark. Because if you have a formula of saying the popularity of each page, which we initialize all fairly, right? So everybody has a 1 here. But we see already there are certain different links. But, could someone see directly who would be probably the winner? Going once, twice. Okay, this. Yeah, okay. And this small toy looks a little bit like, okay, there's one that is getting lots of links. So that is probably the one that makes a race, so the top. And we will see, well, there's some truth to it. But you see also that others are not so far off, or we'll also get interesting points, right? So this is now the idea at scale where you would have to think that computing this now in one iteration will bring us, for instance, to this idea. And there's this interesting formula how you compute this. You would say you have this rank divided by basically how many neighbors now floating out your energy, so to speak, right, with 0.5, which you have to add here. And then have this, each page rank should be basically times here plus times the contribution you receive. And to update this. So this would be the first iteration, trivial example. Now, then we are there. And you can see already your statement is sort of true. He is already, make the winning statement. In a way, you see now, it is important now that this is someone, that is pointed to, and that is where the popularity comes from. But you see also, given it is a very popular site, it also influences on the right? So basically, and this is something which just comes clear through basically another step in the next time step. So when you come, of course, more to iterations, you can now do the computing if you like at home. I skip that here now for the time's sake a little bit and do this more faster. You see that iteratively, you see then that you come to some sites which basically, although everything was equally initialized, that the algorithms then can actually determine over times, not the top one, but also the top two of the sites. And now when you see what we're ending up to, we see also quite surprises on the right. Right, and this is true because basically you see we have the one fellow on the right, but if you look also, then this one is also contributing to the famous part on the right a lot. And it is also not, say, giving a lot of information away from some, let's say, loosely site, but rather on the bottom indirectly gets also again linked via the popular sites to this. So when you have these algorithms, they're for humans not really doable, especially if you now come to billions of that, right? And if you go through, so there will be ups and downs, up and down, and suddenly we have the winner is. But it is close if you think about 1.3.7 and 1.4.4, although it seems very trivial here to do that. But it comes to the indirect relevance through a step you don't see, right? And this is where the iterative approach comes in. And that's why graph application problems are also very tough. And these days, it's even graph neural networks, right? There's also quite nice material that captures in the kind of related elements in a quite nice space, something we can't talk about here, but possibly we're in a deep learning course in the future or by someone else. Hence, graph problems exist. And then you can imagine iteratively means going through the same websites again and again. All what we want to do is understanding who's point to who. So this is something what we can put in cache easily. And you see a little bit, of course, what you do when you have number of machines. You can even speed up with Spark. Number of machines now refers to the sort of worker idea, right? While the head nodes stay the same, roughly 2 or so for resilience, as I said, you would now go up and down in the worker nodes. And with this can also improve now the performance. And, again, take away the message. The idea is here, not that you do this in the simple graph I was showing you, but you do this with 322 million links. Right, then of course it's clear that basically you as a human are not really, following this anymore. And you see also, of course, the benefit now from in-memory cached ideas with the Hadoop engine and Spark. And again, the same problem, although it's graphs, the same problem applies if you now have Apache Spark running on a non-memory intensive computer, you lose the benefits of Spark again, right? So the performance would be much more equal. So in a way, you have to compare this also. You can run Hadoop much more cheaper, achieving these results. If you need, that is maybe good enough for your company, right? Why it needs to be real-time, maybe for stock exchanges here and so, but for ranking web pages, that can be maybe done overnight. This is a decision that the startups industry and also the academics here and there have to take. Is it really worth to pay, let's say, so much money per hour just to have a faster idea and convergence? It is possible with Hadoop. Towards the end, just some examples to think a bit more broader where this is going. And on Thursday, I will give you a really practical demonstration of all of that in a Jupyter notebook. Turns out my lady has another important event, so I cannot be in person. So I will be probably remote. I will also hand out the assignment on Thursday in the 3rd hour. So however I do this, I will see then either the lecture is pre-recorded and then we have an interactive Zoom session. I need to be with the kid at home, but in the end, we will make it that basically we have the session. And just before we go into these practical examples, which will be directly relevant for your assignment, just some fruit of thought, how you would go now use Spark in different areas like Yahoo for news and web pages. You can imagine high throughput computing problem, right? You have tons of news pages. They link here and there to each other, but they're not really depending on a word by word character base on each other. So you can nicely separate them and say, this million of web pages will be handled by this chunk of work, this million of web pages by that, and do your whole operations. Maybe what people are interested in, where they put their cursor along. There's things like actually people track on websites these days to analyze better the behavior of customers. And to analyze this is now something what, for instance, Yahoo does, and with a very specific engine based on Spark for this very specific problem where readers are interested in. That doesn't mean that whole Yahoo is actually having a whole business there. The same is actually true with Facebook, right? They have different specific sub-engines where they do several problems like indexing, likes, and so on. We come to this also in later lectures. Then at Conviva, just to get the across that everything is not always necessarily just data in terms of text or data that is not flowing. Spark streaming, again, we did the idea of now the velocity is quite interesting and get the performance where it maybe can pay off to pay a lot of cash to analyze basically live streaming videos directly from companies. That basically then adheres to the elements what you do. In one respect, you can see also YouTube, right? When you upload a video, it will check these days a lot of things, AI generated content, kids, tons of stuff if you upload to, if you violate basically YouTube or if it's a video that has already been uploaded. So all of these could be taken care of streaming because in a way you break down the whole video into smaller chunks on a minute basis or hour basis and so on. And then you get community strikes on YouTube usually when you do this. Hence, of course, this is an interesting idea and also Conviva in this regard using this with video streaming. Clear Story then is using this in a more interactive way, using this. And yeah, I encourage you to look at some of the examples. So the references show some of the success stories. If you're also interested in HD Insight, they have lots of success stories again and again, like Amazon as well, the AWS. I mean, you had one lecture basically recently where you should just look on all the different cloud providers. You always see also customer stories, case studies, and this is quite interesting to look at. So in other words, these are just customer stories basically of using Apache Spark in real business environments. Finally, now to make the contrast again, we were alluding to something which was scalable. And many of the things we do here in PySpark seem to be scalable, right? So we linked this the last time in the Google Colab. You can even get a pro version for $9.99 or so and get better CPUs and GPUs and so on and do your work, which is essentially true and it works faster. But now this is a very limited environment. You cannot compare this Apache Spark that you run in the Google Colab with the one that we do in a practical lecture 3.1 or so. The general look and feel is very similar, right? It has a different idea of PySpark on the local environment on this particular CPU. And this would not at all actually be ready for big data, right? It still mimics, of course, a cloud in one respect, as we saw the last time. It is still remote. You don't have to install it on your laptop. Everything is nice with PySpark. You can install it, as I showed you last time in lecture 2, and which you also will reproduce in your assignment, also in the Google Colab. But then when we move to basically HD Insight, that's important for you to understand then that this is really distributed. So I will show you basically on Thursday also the idea of tracking this a bit more with MapReduce tasks and different worker nodes and so on. But this is all coming. Of course, then it's still interesting to use it. So I would not say Google Colab is, something that you shouldn't use. If your problem scales until this is fine, then I mean, this is a very nice environment, also thinking about you have basically the chance of having lots of these algorithms used, right? Which are quite nice from the MLlib. As I said, very strong algorithms. But of course, you have a certain limit in scaling, just to contradict again between this. The final point, just a small video, again, summarizing some of the aspects and go a little bit further in terms of what we had in the course. Maybe just for the sake of reference, there's lots of bibliography again, which I encourage you to look at if you want. This is here and there more about HD Insight, where we will talk about also, and in the assignment and so on. So for those of you, of course, I should not forget my strong set of people that are behind me in my research group. I also would like to pinch an idea in the sort of break in the moment, because now I will stop sharing before we go, or basically stop recording before we go to the video.